right. This is where we stopped. 7 excitons at the cost of 1, and now we want to know how did they even know that they have done it. Well, they knew it from transient absorption data, and to understand what they did, it is instructive to follow this schematic that they had presented in their paper. What they say is this: as we saw earlier, in 200 picosecond or so, the hot excitons have cooled down. So, whatever we have beyond 200 picosecond is has got to do with exciton, and here we are talking about transient absorption, right. So, transient absorption beyond that initial decay is quite long lived, and that is entirely due to, well, if I may call it, monoexciton, not biexciton, not anything else. So, what they said did is this delta A, or what as they have written delta alpha, they designated this as B, and here this Nx equal to 1. Nx equal to 1 basically means it is a regular exciton, not biexciton or anything. And then what do you get after this instantaneous excitation? You get this hot electron, well, hot exciton, then biexciton, and so on and so forth. So, what they said is that this instantaneous excitation is designated as A, and this Nx equal to A by B, this is what they call well, that multiplied by 100, that is a percent quantum efficiency for formation of exciton. So, this is what happens when everything is a regular exciton. This is in the initial stage, you have hot exciton, and then you have your biexciton and so on and so forth. So, what they say is that this is a measure of quantum efficiency. And then once again what they did is they tail matched, and they tail matched at 1. Why? Because Nx equal to 1 at long times. And then when after tail matching, in fact, you see the tail matching is done at longer times. Here it is not even 200 picosecond, it is 1200 or more. As we have discussed earlier, excitons can actually have a long component of lifetime. So, here if you go from bottom to up, you actually go from 2.4 times Eg to 3.9 times Eg, 4.9 times Eg, 6.7 times Eg, 7.8 times Eg are superimposed, and at 0 time they are superimposed at a value of 7. Remember, normalization has been done to 1 at long time. So, basically this 1 is B. So, whatever we get from the well, y intercept, if I may call it, well, it is y intercept, it is just that y is delta alpha, that is your efficiency, that multiplied by 100. So, this is how they arrive at 700% efficiency. 700% efficiency might sound strange to people working in fluorescence spectroscopy. Let us not forget that more than 100% efficiency is quite common in photochemistry, right. Number of molecules produced per photon absorbed, that can be more than 100%. The only reason why we cannot have quantum yield more than 100, fluorescence quantum yield more than 100% is that you use 1 photon, you cannot get more than 1, you will always get less actually. So, this is different. Here whatever extra energy has been, so we are using a photon of higher energy, and the excess energy is being used to generate more excitons. That is why we get this 200, 300, 500, 700% quantum efficiency. This quantum efficiency is for formation of excitons, not fluorescence. Is this the efficiency of formation of charge carriers? Actually, no. No, that will come later. And what they have in the inset is that they have superimposed for every case the short time constant obtained by regular fitting and by this Nx normalization, and they have shown that it is just consistent. So, what we have arrived at is that there is a difference between bulk materials and nanomaterials. I mean, there are many differences between bulk material and nanomaterials. In this context, the difference is that for a bulk material, what happens is when you excite at Eg, you have one photon absorption and generation of one exciton. So, efficiency is 100%. Yeah. If you excite at 2 Eg or 3 Eg or wherever, this efficiency does not change. One photon is absorbed and an exciton is generated. That is what happens most of the time in bulk. And the inset here is the actual efficiency of charge carrier generation, and that efficiency has been worked out already. It turns out that it can be maximum of 0.44. As you see, you excite at very high Eg value, you get nothing. You excite at 0, which means you do not excite, then of course, you get nothing. When you excite at Eg, that is when you get the maximum efficiency, because you have excited more than Eg, then non-radiative processes take over. See, in all the discussion so far in the previous module and this one, we have not for once talked about other kinds of dissipation. Well, we have in a way, because they talked about cooling, but we really did not think about it so much. We kept thinking that we generate one exciton somehow, that exciton will give us one charge carrier. It is not necessary, they can recombine. They will recombine, right. So, the competition always is between recombination of electron and hole by themselves and their separation by applying an potential difference. So, 0.44 is the best one can do. I am talking about efficiency of charge carrier generation. Efficiency of charge carrier generation can at best be 0.44 in bulk. In nanoparticles, however, what one can think is that if you use smaller Eg nanoparticle. So, this plot is I understand it in a different way. If you use photons of higher and higher and higher energy. So, compared to that, this Eg is smaller and smaller and smaller. So, what we are saying is that as you use material with band gap that is much smaller than the energy of the photons that you use, efficiency can in principle go up. Which efficiency? Efficiency of charge carrier generation can in principle go up to 100%. Okay. That is the ideal scenario. This is the reality. In these two modules, we are going to take the names of certain people who have really made advances in this field over the last few years. You must have heard of Nozick, because one of his works actually made it to the newspaper, I think last year or year before. So, what Nozick's group showed was that this is what you expect, a stepwise increase in efficiency of charge carrier generation, and well, efficiency quantum yield, and then efficiency of charge carrier generation is written. This is what they get for PBSE quantum dots. This is what they get for bulk PBSE. So, see, bulk PBSE also it is not flat, right. What is the expectation? Quantum yield should be just the same. That is not correct. And if you look at the efficiency of charge carrier generation, in bulk it is 0.2, in nanoparticles it is 0.4. It is definitely more, but the picture is really not as rosy as we might have thought it is. It gets doubled, it does not get 100 times, but nevertheless the efficiency of charge carrier generation does go up if one goes from bulk material to its nanoparticles, and that is what has made this quantum dot solar cells very attractive. These are two kinds of quantum dot solar cells that are commonly studied, commonly made, Schottky barrier and p-n heterojunction. In Schottky barrier, what you have is you have glass ITO. ITO is a transparent electrode. So, light has to get in, right, and but at the same time there has to be an electrode. Inside that you have this semiconductor nanoparticle film, and then you have the other electrode, well, calcium aluminum, that is what it is. That is what gives you the Schottky barrier. and in the other one you have a p-n junction. So, you have a p quantum dot layer, you have an n quantum dot layer, and rest of it is pretty much the same. There has been a lot of study of not only efficiency, but also ultrafast dynamics of charge carrier formation in quantum dot solar cells. This in itself is has become a very hot field of research over the last 10 years or so. Before quantum dot solar cells, people used to talk more about dye sensitized solar cells. Well, again let me digress a little bit. Why is it that we need all this? I mean, solar cells are there all around. We can see solar cells. I mean, from here if you go to well, look at the roof of almost any building, you see solar cells. What is the need of further research in solar cells? The problem is the solar cells are actually very expensive. Solar energy works because of huge amount of government subsidy. It is really not a commercially viable proposition even now, and then it is very easy to break those cells also. Somebody gets unhappy with solar energy, can go with a stick and mash up the cells, and it is very expensive. So, one approach that had been taken was we will use a dye, excite the dye, and that dye is going to transfer its energy into things like titanium dioxide nanoparticle, and then charge carrier generation would take place. And there has been a lot of work in from late 90s. Well, of course, people started working with things like porphyrins and other dye molecules. It was found out that your dye molecule has to have a COH functionality, otherwise it cannot anchor itself on titanium dioxide nanoparticles. So, people tried other things like vegetable dyes. Somebody proposed goat blood that contains a lot of dyes, and so on and so forth. But there is a problem with dye sensitized solar cells. Dye sensitized solar cell kit can actually be bought for I think few hundred rupees or maybe a couple of thousand rupees. You can buy it, everything will come, you assemble and you are done. It is very nice thing to demonstrate. The problem is this: the whole idea of this your dye sensitized solar cell comes from photosynthesis. In photosynthesis, you have light harvesting, you have a reaction center where charge separation takes place, and that is how it works. So, if one can mimic photosynthesis before the step of production of glucose, then one can harvest sunlight, and all these processes are ultra fast, right? Absorption of light, of course, and then there is always this FRED that takes place, and electron transfer, everything is ultra fast. That is why the ultra fast community got into this field. Now, the problem is this, that even chlorophyll, by the way, is something that degrades in sun, but the advantage of a plant is that it is a living thing. So, it can grow more leaves, it can produce more chlorophyll. Dye sensitized solar cell cannot grow, cannot produce more dye, and it will be really messy if you have to change that dye all the time. That is why whatever dye is used in dye sensitized solar cell so far is found to be not stable to the point of satisfaction in sunlight. So, the cell would work maybe for 1 hour or 2 hours or maybe 2 days, 5 days, and not anymore. So, it is once again not a very practical thing. That is why focus moved to solid state solar cells, and quantum dot solar cells have been explored for a long time, because quantum dots are more stable than dyes, and secondly what we saw is, being nanoparticles, there is this advantage of formation of multi-excitons. Okay. So, ideally this module should have ended here, but let me just for the sake of completion also go ahead and say that quantum dot solar cells, as many of us would know already, are slowly making way, or maybe not even slowly, for another kind of material, a solar cell with another kind of material, and that is perovskites. Again, the problem of perovskites is stability so far. Two problems. One is that perovskites contain lead. So, one major focus has been to make perovskite without lead. The other issue is stability, stability to water, moisture, stability to light, and so on and so forth. But quantum dots, perovskites have turned out to be very, very promising. So, once again let me just show you a piece of data, not really going into the detail of perovskite, but there is another reason why I want to show it. Moser and co-workers, and this is a paper that has been published this month, 2020. So, again perovskite quantum dots have been made, you can see the images here, and generally when you have perovskite quantum dots, you see squares, nice squares, they are very good looking. Only last week there has been a paper from the group of Narayan Pradhan, where they have made perovskite quantum dots of shapes other than square. That itself is an interesting advance. But here since it is a nanocrystal anyway, you have similar absorption and PL spectra that you expect for nanocrystals. So, what Moser and co-workers have done is that they have studied ultrafast dynamics in this perovskite nanocrystals using transient absorption as well as fluorescence subconversion. But the fluorescence subconversion data here actually looks like transient absorption, does not it? I am talking about the top panel. There are two axes, actually three axes. Third axis is pointing towards you, intensity, and the two axes are time and wavelength. Okay. So, the way it has been done, I think I mentioned it in the passing when we talked about fluorescence subconversion, is that they have used a different kind of crystal. In the some frequency generation crystal that they have, the optic axis is horizontal, and that makes it possible for some frequency generation over a broad band. So, what you can get is that you can get the fluorescence spectrum, entire fluorescence spectrum at whatever delay you want. Rest of the instrument is same. There is a delay which delays the gate pulse, there is an excitation pulse. The only difference is the fluorescence is focused onto a some frequency crystal along with the gate pulse, where the some frequency crystal allows phase matching independent of frequency. So, for a given delay you can get the entire fluorescence spectrum. That, as we understand, makes life much simpler, makes data acquisition maybe 100 times or 1000 times faster. So, that is what they have done, and what is of interest here is that if you look at the transient absorption time evolution and fluorescence subconversion time evolution, they are more or less the same. Once again, as you go higher in energy of pump or excitation wavelength, you get this ultrafast component, which is missing when a lower energy pump or excitation is used. So, once again very similar hot exciton dynamics is observed here, and what they have been able to do here is that they have been able to show what is the spectrum of the biexciton, and this also tells us that whatever we have discussed earlier, that is not complete, because here even biexcitons emit. It does not have to wait to get to exciton level. If biexcitons emit, that means what they have recombined, they are not there anymore. So, not all biexcitons are going to produce excitons that we had expected, right. The light will be emitted. So, they have been able to separate these two, and they have been able to propose a interestingly, the model they have proposed is very much like a model that we would encounter for molecules, but that is because we are using a particle in a box model here anyway. To close this discussion, what I want to say is this: there is more to life than even biexcitons. We have talked about excitons, we have talked about biexcitons. You can have things where that balance is not there. In excitons as well as in biexcitons, what do we have? Number of holes is equal to number of electrons, but there are other particles, and these are actually known. It is not as if this is new discovery. Biexcitons have been known for many decades. Similarly, what is also known for many decades is trion. Trion means one hole 2 electron or 1 electron 2 hole. you have a Biexciton, somehow an electron has been lost to a defect or something like that. And in this paper published last year by Professor Hiren Ghosh's group, what they have done is that now they have worked with a 2D material MOS2 monolayer, and it is not even homogeneous. This is MOS2 monolayer with gold nanoparticles, and what they have been able to show using transient absorption very elegantly is what is it that happens. They have shown that in 500 femtoseconds you get the exciton, then 600 femtoseconds the exciton can actually transfer the energy to gold nanoparticles, or you can get trion in 1.2 picosecond. How they got trion? For that we will have to read the paper. We are not going to discuss, this is quite a loaded paper. This cartoon is only a summary of what is there, and then from trion it takes 3.7 picosecond to transfer the energy to gold nanoparticle. Well, when I say takes 3.7 picosecond, perhaps I am not really being exact, the time constant is 3.7 picosecond. So, let me just say that the scope of study of ultrafast dynamics in nanomaterial, we have talked about plasmonic nanomaterial, we have talked about semiconductor nanomaterial, we have talked about perovskite. Well, we have shown you the data on perovskite nanocrystals, and here we see 2D material. The scope is infinite at the moment. A lot of new things are there that have not been explored earlier, and using ultrafast techniques one can explore them and learn things that are interesting definitely from the fundamental research point of view, and possibly also to devise newer applications like what we saw application in quantum dot solar cell. So, that is where we close the discussion of systems as such. We will have maybe 3 more modules in which we are going to talk about other kinds of ultrafast spectroscopy. Because in so many lectures we might have given the impression that ultrafast spectroscopy means transient absorption and femtosecond upconversion. It is definitely not. There are many other techniques. We will not be able to go into all of them. Fortunately, if you understand how transient absorption works, then you can understand most of the other things. So, we will talk about only 2 kinds of experiments. One is 2-dimensional spectroscopy, and the other is surface some frequency generation. That is what we will do over the next maybe 2 or 3 modules. For now, this is it.